Yes, please go.
So thank you very much for the invitation to speak here. Yeah, this talk is not going to be very related to the two last topics, I guess, of this workshop. It's more related to the BPS states. I want to let's see. So I want to say some things about non-perturbative topological string theory, and in particular the way it interacts with BPS states. Right. So over the last years, I think sort of a rather elegant picture is emerging for non-perturbative string theory, and there are many people who have contributed to this picture from various angles, and so the names here are just, I guess, a subset of the people who have done something in this subfield of non-perturbative topological string theory. So in particular, this what I'm going to say here is going to be related to the angle of a paper by Alim, Sahan, Teschner, and Tully, and which is related sort of on the mathematics side by a couple of papers by Bridgeland. And people have approached it from different perspectives as well. So it's also very much related to a set of ideas, by Alexander Persson and Piolin in the context of NS5 brains. So in this talk, I will try to explain this picture from a gauge theoretic perspective that is very much based on a couple of papers. Well, at least the base of it is related to papers by Giotto, Moore, and Neitske, as well as Nekrasov and Shatashvili. And in this last line, so these are the papers of mine which I will try to explain. So we're going to start out in 4 dimensions, actually. So since this is a rather broad workshop, I thought I would start with giving some introduction, sort of a more basic introduction to these topics. In particular, so in 4 dimensions, there is a really nice class of n=2 theories, and this class of n=2 theories is called class S. And so this class is distinguished by the fact, so for every n=2 theory, there is a corresponding Seiberg-Witten curve. The theories of class S are distinguished in the sense that these theories, for these theories, the Seiberg-Witten curve is a covering, a degree k covering, which may be ramified over another curve, which I will denote by C. It's sometimes called the UV curve. It encodes all the UV, the microscopic couplings of this n=2 theory. And the number k corresponds to the rank of the n=2 theory. So it corresponds to the gauge group, SUK. So in this class S, there are the conventional n=2 theories, like the pure SU2 gauge theory, the Seiberg-Witten theory. But there are also sort of more interesting theories, like, for instance, the Minahan-Nemeshansky theories, which are intrinsically strongly coupled. That is, they don't have any sort of, there is no place where they're weakly coupled. Right, so these theories of class S are geometrically characterized by this Seiberg-Witten covering, the Seiberg-Witten geometry, where the Seiberg-Witten curve sigma is embedded in the cotangent space of C. So in this talk, I will usually take a local coordinate, little x on C, and y in the fiber direction. So that means that the Seiberg-Witten 1 form, which is the canonical 1 form in this geometry, is just defined by lambda is equal to y times dx. Right, so these n=2 theories in the infrared they're characterized by a moduli space of vacua. And in this talk, I will be interested particularly in the Coulomb branch of this moduli space, which I will denote by B. So these four-dimensional theories, we could reduce them. We could place them in the background R3 times a circle, where the circle has a radius R, capital R. That means we end up in 3 dimensions with an n equals 4 theory, which in the infrared at low energies may be described as a 3-dimensional sigma model into a certain moduli space. And this moduli space, for these n equals 2 theories of class S, this moduli space is the Hitchin moduli space. So this is the moduli space which is characterized by these PDEs. So these are not going to play a very important role, so I won't say too much about this, except that all of this is defined in terms of this UV curve C. So A is a connection in an SUK bundle over C, and this phi is the Higgs field, so it's a holomorphic 1 form with values in the anamorphism bundle. Right. So this Hitchin. So what is important is that this Hitchin moduli space, it's a hyperkähler moduli space, so it has a CP1 of complex structures. So the CP1 I've denoted here as this sphere. I've parameterized it by this variable psi, and there are sort of 2 special points in this P1, the North Pole and the South Pole, because at these points this Hitchin moduli space has a special integrable structure. It has the integrable structure of a torus vibration over the Coulomb branch B. So this is called the Hitchin integrable system, and the moduli space with this complex structure is often denoted as M Higgs. So it's the moduli space of Higgs bundles. If we are at other points, so if psi is not equal to 0 or infinity, then this moduli space has a different, so it has a different complex structure, it has a different description, it has the description as the moduli space of flat connections, but complexified connections. So these are SLK, C connections on this UV curve C. So that's the description for any other point in this on this sphere. So how is this all related to topological string theory? So the relation comes if we basically lift this n equals 2 theory to 5 dimensions. So if we study, instead of the 4-dimensional theory, if we study the 5-dimensional n equals 1 theory on R4 times a circle, which now has a different radius, which I've denoted by beta here. Because once we do that, this 5-dimensional theory, it has a Seiberg-Witten curve as well. And this Seiberg-Witten curve plays a role in the topological B model. So there is a certain Calabi-Yau, which is modeled on this 5-dimensional Seiberg-Witten curve. And by mirror symmetry, this is related to a certain toric Calabi-Yau. Which then again by the geometric engineering story is related to the 5-dimensional n equals 1 theory that we started out with. So what is going to be important is this B model picture, basically where this 5-dimensional Seiberg-Witten curve plays the role of the mirror curve. So it's a curve now which is embedded in C star times C star. So these C stars, I give them local coordinates capital X and capital Y. And the Seiberg-Witten 1 form in this context, it has the form log of capital Y times d log capital X. So some more background. So what we are interested in is we're interested in considering these gauge theories in the so-called omega background. So we're not just considering them plainly in the background R4 or R4 times S1, but we look at some more complicated geometry. And so in 5 dimensions, this 5-dimensional geometry is described as a C2 bundle over this S1. So we consider a bundle where, so if we take local coordinates, Z1, Z2 for the C2 coordinates, for the complex coordinates, and X5 for the circle coordinate, then if we make a loop around the circle, then basically we rotate with phase epsilon1 and epsilon2 around these 2 planes. So this is illustrated in this picture to the right. Then to make this a supersymmetric background, you'll also need to do, rotate the internal, the R symmetry SU2. And what we want to do is we also want to take a gauge rotation when rotating, when sort of going around the circle. Well, with these ingredients, you can write down an index. So this 5-dimensional, the partition function of this 5-dimensional theory, it can be reduced to some supersymmetric quantum mechanics and on the circle, and then it can be computed by some supersymmetric index. Well, this supersymmetric index is known as the Nekrasov partition function, and if we reduce this theory to 4 dimensions, so if we take this beta going to 0, then we end up with the 4-dimensional n equals 2 theory in the omega background, which I will denote by C with a subscripts epsilon1 and epsilon2 in this talk. So this is a way to regularize the partition function of the super-Yang-Mills theory and to be able to assign it a partition function. Oh, right. So this is what I've basically said here. So this object C, Nekrasov in 5 dimensions, that's this index, this 5-dimensional index. And if we go to 4 dimensions, we get a partition function. And this the log of this partition function, this Nekrasov partition function, it starts out with a term which is divergent in epsilon1 and epsilon2, and which is proportional to the Seiwert-Quantum prepotential, and then it has terms which are less singular in epsilon1 and epsilon2. Right. So this is the important, well, this is one of the important objects in this talk. So what I'm going to do more today is I'm going to, although this picture can probably be generalized to the whole the whole omega background, I'm going to focus on what is called the half omega background. So what I'm going to do in this talk is I'm going to set one of the epsilons to 0, and the other epsilon I'm called epsilon, as in this picture. So that means we consider a C2 bundle over S1, which is governed by this identification, which is defined by this identification. Well, if you have, well, it might be that you've seen this background in different contexts. So sometimes sort of the 3-dimensional part of this background is also denoted by C times with a lower script Q times S1 beta, so a twisted background. So that's exactly the same thing. Right, so why is this background interesting? Or, well, what is one of the reasons why this background is interesting? So as we've seen, the n equals 2 theory is very closely related to this Hitchin integrable system. If we turn on this omega background, this parameter epsilon, then it turns out that this quantizes this Hitchin integrable system, where the quantization parameter is equal to epsilon. So the quantized Hitchin Hamiltonians, so an integrable system is characterized by Hamiltonians, So in this background, the theory is dual to some quantized Hitchin integrable system. So, so they're quantized Hitchin Hamiltonians, and these quantized Hitchin Hamiltonians, they are described by so-called quantum curves. And so these are quantizations of the cyberquantum curve. So in 4 dimensions, the quantization of the cyberquantum curve is given by some differential operator, which I will denote by d epsilon. And so one of the famous examples is the pure SU2 super Yang-Mills, where this differential operator has this particular form. So it's a second order differential equation. It has parameters, of course, epsilon. It has the scale lambda in it, and the Coulomb parameter, which parameterizes the Coulomb branch of this SU2 Yang-Mills theory. And this differential operator is very closely related to the Mathieu differential equation. There is a change of coordinates which brings you to the Mathieu differential equation. In 5 dimensions, because these cyberquantum curves, because they're embedded in C star times C star, that means that their quantizations become difference operators, which I will denote by capital D epsilon. And for instance, a simple example, the 5-dimensional pure U1 Yang-Mills theory corresponds to a difference operator, which is of this form. So this pure Yang-Mills theory is something that we will come back to later. So that corresponds to the resolved conifold geometry in topological strings. This Q, this Q is the exponentiated Kähler parameter of that geometry, and X is the coordinate, the local coordinate on C. Right. So if we put a theory in this half omega background, so remember that we have one plane where we have this omega deformation and one plane where there's no omega deformation. So that means that if we consider this theory at low energies, we're basically going to reduce our theory. If we started out with a 5-dimensional theory, it will reduce to a 3-dimensional n equals 2 theory on the complex plane times this S1 beta. And in the limit where beta goes to 0, it will reduce to a 2-dimensional theory. And at low energies, that means that this theory will be described by an effective twisted superpotential. So this effective twisted superpotential is basically a limit of the Nekrasov partition function that we've defined before. And in terms of the quantum integrable system, this will correspond to a so-called Yang-Yang function. So this is all predicted by the work of Nekrasov and Shatashvili. Right. So one more comment about the relation to topological string theory. So this Nekrasov partition function is well known to be related to a certain topological string partition function, and it's equal to the refined topological string partition function. Then there is another thing that we want to do later in this talk, and that is we want to consider certain defects in these theories. So from the perspective of topological strings, we would like to consider certain branes which we insert in these geometries. So on the A side, this will be a so-called A brane. On the B side, these will be B branes, and these branes, their moduli space is so the moduli space of these B branes is really this cyberquantum curve. So this is important. So by geometric engineering, these brane insertions, they correspond to surface defects, and we will be particularly interested in the surface defects that wrap this omega deformed complex plane. So the surface defects, they have vacuum excitation values, which are denoted by psi. And these psi's, they are solutions to this quantum curve equation. So they're solutions to this, in this case, difference equation defined by the quantum curve d epsilon. Right, so this is all very well known. It's basically the story as it was about 20 years ago. But in the last couple of years, there were, various new insights have been obtained, and new questions have been posed. So first of all, there was this discovery that there is this really large, there is this large interesting class of n=2 theories of class S, which is interesting in the sense that it contains many more theories as the theories that we knew 20 years ago, some of which are intrinsically strongly coupled. Moreover, in these papers, especially the papers by Giotto, Moore, and Neitzke, many things were computed and for this class of n=2 theories, and such as BPS spectra, so BPS, BPS particles and other kind of BPS objects. They were all studied for these classes in terms of this, in terms of the Hitchin moduli space. And what played a really important role in this work was the notion of a spectral network. And this is so the spectral network will play an important role in this talk as well. So I will introduce that in the next slide, I think. But let me first say, so what more happened? So also by other people, so these partition functions and so these theories, these n=2 theories, they were related to these quantum Hitchin moduli spaces, and by certain sets of nice dualities, which I will come back to in a few slides as well. And then there was the realization that this topological string partition function of this Nekrasov partition function that we've defined before, that this is not the complete answer at all. So that this is an object which is not well defined in certain sort of regions of the epsilon plane, and hence this cannot be the complete answer. This cannot be the complete non-perturbative topological string answer. So through various dualities, various proposals came up for what this non-perturbative partition function should be. Right, so let me introduce to you now what a spectral network is. So let me say that in the context of four-dimensional n=2 theories, these objects are called spectral networks. In the context of the five-dimensional theories, these are sometimes called exponential spectral networks or exponential spectral BPS graphs. And so in the context of the four-dimensional world, this was all defined by Giotto, Moore, and Neitzke. In the context of the five-dimensional setup, there is a long series of works by Banerjee, Longhi, and Romo, which studies various aspects of these exponential spectral networks, and in particular computes the BPS spectra for various examples, various interesting examples of five-dimensional n=1 theories. Right, so what is a spectral network? So remember that these n=2 theories, they were basically characterized by this data. So we had some ramified covering, this Seiberg-Witten curve. So that was a ramified covering over the UV curve C. And another important ingredient is this one form lambda. So the spectral network is defined exactly in terms of this data. So the spectral network, it's a real one-dimensional graph on the UV curve C, and it's defined by a certain condition. So it's defined by this particular condition. So what does that mean? So we can restrict this lambda to the case sheet of the covering, and we can subtract lambda, which we restrict to the case sheet of the covering, so that this object then is still a one form. And so suppose that we draw a certain curve, a one-dimensional curve on C, which has a tangent vector v, then this curve is part of the spectral network if this contraction of lambda j minus lambda k with this tangent vector, if it has a certain phase, if it is a certain phase theta. So right, so given any sort of n equals 2 theory in 4 dimensions, that is, we can consider the corresponding UV curve C. We can consider all kind of any sort of arbitrary curve on this, an arbitrary trajectory, I should maybe call it. So this one-dimensional trajectory on this curve C, and it's part of the spectral network if this constraint is obeyed. So one of the simplest examples is, so I've actually not given the geometry here, but one of the simplest examples appears in what is sometimes called the 82 geometry. So in that case, the sigma is, maybe I should write it down. In that case, sigma is defined just by y squared is equal to x squared minus m. So this geometry, so where m is just a fixed parameter. So this geometry, it has, it's a degree 2 cover over the complex plane, and it has 2 branch points. So these 2 branch points, I've denoted by these orange crosses here. And we're especially interested in the trajectories of the spectral network that leave from these branch points. And it turns out that in this geometry, if you take theta to be, so there turns out to be one particular phase, which I've denoted by the critical phase, theta critical, where some of these trajectories start to overlap. So they form a so-called saddle trajectory. So it turns out in general, if you have a simple branch point, then there will always be 3 trajectories which come out of such a branch point. There are 3 trajectories which obey this constraint. But the way that they come out is determined by the phase theta. So if we change theta, then these trajectories will come out in different ways. So the generic, if we take some generic phase, then these 3 trajectories, they may come out like this. So there will be 2 trajectories going up and there will be 1 going down. But then if we change this phase theta, it may happen that some of these trajectories start to overlap. And in this geometry, there are exactly 2 phases for which that happens. So one I've denoted here, the other looks exactly the same. So if we make the phase theta even larger, then they disconnect again and they go the other way around. So it turns out that these spectral networks, they're interesting for various reasons, but the reason that they were defined by Kyoto-Moore-Nitschke was that they encode the BPS particles of these n equals 2 theories in a rather elegant way. Namely, exactly when there is such a critical phase, there is a corresponding, so there is the corresponding saddle trajectory, there's a corresponding 1 cycle on the covering, and that hints at the existence, at the appearance of a BPS particle. And this BPS particle will have it will have this phase theta. Well, maybe I should say this here. It has the phase theta c. So, sorry, that is the argument of the central charge of that BPS particle has phase theta c. Well, maybe I should make a few more remarks about this. So this is a very, very simple example. In general, if you consider n equals 2 theories offering k is equal to 2, so SU2 theories, then the corresponding spectral networks are not too complicated. Whereas if you go higher up in rank, it becomes kind of a mess in most cases. And the same is true if you go to 5 dimensions. So for 5 dimensions, you can define these networks in sort of exactly the same way. But in that case, there will be sort of the additional difficulty that there are logarithmic branch cuts, which I might come to later. So there are some subtleties, but basically the same idea holds there as well. And so also in 5 dimensions, the networks are in general very, very complicated. Right, so the second thing that I wanted to come back to is the relation of these n equals 2 theories in the omega background to the Hitchin modular space, because this is another ingredient which is really important to introduce a more general object than this Nekrasov partition function that we've introduced before. And so insights come from a certain duality chain, which came up, which was sort of studied in a paper by Nekrasov and Witten a couple of years back. So this duality chain starts out with the idea that that if we consider, so I'll go through this duality chain in the 4-dimensional setup. So I'll forget about the additional S1 for a moment, but it's easy to introduce that later on. So in the 4-dimensional setup, we had the background C times this omega deformed plane. And now there is the remark that instead of C times the complex plane times this omega deformed plane, we could instead consider the complex plane times a cigar geometry. So basically we deform this omega deformed plane into a cigar. We take a metric, which is of this kind, where the FR, the function FR, it goes like R squared when R is very small, and it goes like some constant rho if the radius becomes very large. So this cigar geometry, so we have this, so instead we can consider this cigar geometry. This will not affect anything. So this Nekrasov partition function, it's computed in a certain twist, so it will not be sensitive to particular the metric that we take. So we can just study this geometry instead. Well, now the important ingredient from this paper of Nekrasov and Witten was that we can actually undo this omega deformation, at least if we're away from the origin of this cigar. So this is drawn here. So this part of the geometry, which is still very close to the cigar, that's still omega deformed. But if we're away from this origin, then we can deform. So we can undo this omega deformation, and we can undo it in return for a field redefinition. So our fields will be redefined, and the epsilon will be a parameter in this field redefinition. Now, if we compactify this whole setup now to 3 dimensions, so if we make this circle, this additional circle of the cigar geometry, if we make it very small, then we will end up again with a three-dimensional sigma model. If we wouldn't have this additional piece, this omega deformed piece, this would be just a standard three-dimensional sigma model into the Hitchin modular space that we saw before. But now we have this additional ingredient in the geometry. We have this additional omega deformed part of the cigar, and so the claim is that in the sigma model, this piece of the geometry will translate into a certain brane. And branes in the Hitchin modular space, they are defined by complex Lagrangians. What we will end up with, this geometry which is C times an interval. And now we will have two boundary conditions. We have a boundary condition at infinity. So this boundary condition will be determined by the boundary condition that we had in the sort of original n=2 field theory. But we have an additional boundary condition, and this additional boundary condition, it will depend on this omega deformation parameter epsilon. Right. So if this argument of epsilon is related to theta in this particular way, if it's related, yeah, then in that case, this background, it preserves for supercharges. And that means that that if we let this interval, if we now reduce this interval just to a point, we will end up with a two-dimensional n=2,2 sigma model, which will now not go into the full Hitchin modular space, but just into the base, this Coulomb branch, which is the base of this integrable system, and it will have it will be characterized by superpotential. And by the work of Kapustin, Rosansky, and Salina, this superpotential, it is the generating function for this difference of Lagrangians. So if I have two Lagrangians in a certain two complex Lagrangians in a complex plane, in a complex space, then I can associate to that a certain generating function, and so that means that this superpotential of the n=2,2 sigma model, it's characterized by something very geometric in this Hitchin integrable system. Right, so perhaps I should note that this boundary condition at the very end of the cigar was not very explicit when we were discussing Nekrasov partition functions, but now it is very explicit. And because we've gone to the infrared to get to this picture of the sigma model, it means that this Lagrangian, it will be characterized by a certain point in the Coulomb branch, so which I will denote by U here, but it will also be characterized by this phase theta, and this is something which will become a little bit more clear, I think, later. But yeah, from this perspective of this sigma model, this three-dimensional sigma model perspective, these Lagrangians, if we want them to preserve these supercharges, then that means that these Lagrangians that they have to be these parameters epsilon and theta, they have to be related by this particular constraint. Well, what we should take out of this is that this three-dimensional, this should be the right. So the five-dimensional theory in this half omega background, which reduced effectively to a three-dimensional theory on C times S1, as well as the corresponding two-dimensional theory, they are governed in the infrared by an object, a certain superpotential, which is labeled by the Coulomb parameter U, as well as this phase theta. So that is the important thing that we get out of this duality chain. So note that this is slightly, well, it has more parameters than this Nekrasov partition function. So one of the questions now is, okay, so how is this superpotential that we got from this Nekrasov-Rosly-Shatashvili perspective, how is that related to this superpotential that we get from this geometric perspective? And how can we define, I mean, how is this object really defined in terms of the geometry? So I'm going to say a couple of things about this. So this object, it turns out, this superpotential, which depends on u, these labels u and theta, it may be obtained at least if we have an expression for the effective twisted superpotential, then the superpotential may be obtained as a Borel resummation of the epsilon expansion of this known expression, where we Borel resum in this direction theta. So maybe I'm not sure whether everyone is familiar with the Borel resummation, but let me just remind you that if we have some divergent some divergent series expansion of a function f of epsilon, so suppose it has this series expansion where this coefficient cn, where they go like n factorial. So in other words, f, this function f is has a Chevret power series expansion, then its Borel transform is defined. Oh, there is a series expansion here missing. Sorry, some missing here. But basically, the coefficients they are divided by these powers n factorial, and often this Borel transform then is a convergent object, which means that we can integrate this Borel transform along a certain ray which has phase theta, and the resulting object, this Borel sum of f, it then has exactly the same series expansions as the function of f that we start out with if epsilon is small, but it's an exact expression in terms of epsilon. So we might think of this Borel sum as some kind of trend series, where not only we have powers. Well, maybe I should have. Well, this t is the same as the epsilon above. So not only we have powers in epsilon or in t in this notation, but also we have other kind of contributions corresponding to, in physics you would call these non-perturbative instantons, and there might be some log expression which corresponds to zero modes if we have instanton anti-instanton collisions. Right. So so one of the things that characterizes this object WU theta is that it is related to the object that we already knew, at least in a case that we can compute this object as its Borel summation in a direction theta. So what's interesting about this Borel sum is that it's not defined everywhere. So there are critical directions where you cannot compute, where the Borel transform has singularities. So so if this is the Borel plane, then there might be some isolated rays. There might be some rays which accumulate to a certain rate, and along these special rays, we cannot do this Borel sum. So otherwise, this object, so it's piecewise constant in this angle theta, but if we cross such a critical ray, then this object jumps. So the interesting thing is that these critical directions, they exactly correspond to the phases of the central charges of the BPS particles that we have in the field theory. So you might remember that we introduced these spectral networks, and that in these spectral networks there were critical phases where some of these trajectories started to overlap, and we got these saddle trajectories, which corresponded to BPS particles. Well, it turns out that these critical phases are exactly the critical directions of this Borel sum of W. So that means that we get this really nice picture that this more general object, it not only encodes this Nekrasov partition function, but it also contains the complete BPS spectrum of the corresponding gauge theory. So maybe to make the relation to the Nekrasov partition function a bit clearer, because so far we've really only Borel resummed along different directions, but we have not seen that we recover the Nekrasov partition function as well. So at which phase do we encounter this Nekrasov partition function? Well, it turns out there is there is a special critical phase, I should say, which we sometimes call the Vengeful-Nielsen phase. And this Vengeful-Nielsen phase is characterized by the fact that it's equal to the argument of the central charge of the W boson. And at this phase, the spectral network is very elegant in the way that, in the sense that most of the trajectories in the spectral network are saddle trajectories. So this is an example of such a Vengeful-Nielsen network for the pure n=2 theory. So in this case, you see that there is a saddle trajectory here as well as here. So that means that the spectral network, it consists of a lot of compact, so it encodes a lot of compact trajectories, and all of these compact trajectories together, they encode this W boson. So we have that this new object, the superpotential WU, at the Vengeful-Nielsen phase, is exactly equal to the Nekrasov-Shatashvili expression W. Right. So you could wonder sort of what are these boundary conditions? What are the corresponding boundary conditions that we have at infinity to these various phases? And it turns out that for this Vengeful-Nielsen phase, the corresponding boundary condition is just a standard Neumann boundary condition at infinity. So that this we take Neumann boundary conditions for the parallel components of the gauge field, and Dirichlet for the perpendicular boundary conditions. But in the infrared, as we've seen, this boundary condition is specified by the point where we are on this Coulomb branch, by a polarization of sigma and the phase theta. So how do we define the corresponding Lagrangian? The Lagrangian that corresponds to this choice of parameters. Well, this Lagrangian, we can define it in terms of a set of Darboux coordinates. So this Hitchin-moduli space, in particular, it has a complex symplectic structure, and it turns out that there is to each phase that we choose, there is a natural canonical choice of Darboux coordinates on this Hitchin-moduli space. And in terms of these Darboux coordinates, which are associated to these phases, this Lagrangian is just defined by the constraint that the B coordinate, the complex B coordinate, is given by 1. So for a generic phase, so this is what is drawn here is a diagram of a phase diagram. So it encodes, so all of the arrows in this diagram correspond to critical phases. So that is where there is a corresponding BPS particle in the quantum field theory. And so if we're at a generic phase, so at a generic phase, that means a phase where we, in particular, where there's no BPS particle, and where we can do this Borel sum, at such a generic phase, you can define these, you can find these Darboux coordinates, and they turn out to be of a certain Fock-Goncharov type. So they turn out to be what is known as cluster coordinates. At the special phase theta Fn, where all of these rays are coming together, that's a so that's a at this phase, at this phase, the coordinates are of what is called a Vengeful Nielsen type. So these are really sort of in various examples, they are the Vengeful Nielsen coordinates as you might know them, the length and the so the lengths of the twist coordinates as you might be familiar with. Well, there is a whole story behind these coordinates, but I won't say too much about that in this talk. In particular, these coordinates, they can be obtained again from these spectral networks using a procedure which is called apollonization. But what's important is that so these Lagrangians, these boundary conditions, these infrared boundary conditions, that they can be described in a simple way in terms of Darboux coordinates, which you can extract from the spectral networks. There might be a slightly sort of easier to understand way to understand what these spectral coordinates is, and that is by saying so. So these coordinates we can evaluate. These are coordinates on the Hitchin modular space, so we can evaluate them on any flat connection. Remember that this Hitchin modular space had generic values for psi, had this description as a modular space of complex connections. So we can evaluate that in particular on the connection that corresponds to this difference or differential operator, the quantum curve d of epsilon. So I've denoted that particular connection by Namla-Oper because to such a quantum curve, there is one can associate what is called a connection, which is called an Oper connection. Well, in any case, so these coordinates evaluated on these quantum curves, they have the form of quantum periods. And these are exact quantum periods in the sense that that they can be obtained by a Borel sum again. So whereas, so suppose that the surface defect Vev, that it has this particular form, then this coordinate, the spectral coordinate, if we evaluate it on Namla-Oper, then it has the form of a Borel sum in the direction theta of the same function S integrated over the corresponding cycle gamma. So these are the usual quantum periods, but now Borel sums so that we get exact ones. And in terms of these coordinates, the superpotential, which was the generating function of the difference of these complex Lagrangians in the Hitchin modular space, the superpotential, which was defined in terms of the geometry of this Hitchin modular space, it now has a very simple form. In particular, so the Darboux A coordinate, if we require that to be equal, so if we define these new Coulomb parameters A theta by this relation, and then we expressed the B coordinates in terms of these A thetas, then the object in the exponential, that will be exactly the derivative of our superpotential W. So this is a way, this agrees with previous sort of non-exact answers for these for the effective twisted superpotential. But now we've made this into a non-perturbative object, which depends on theta. And another way to say this, at least geometrically, is that what we're really, so that's in terms of this language of the generating function of the difference of these complex Lagrangians. It's that since one of these Lagrangians is the so-called, what is called the space of opers, it means that this superpotential is now the generating function of opers in these Darboux coordinates, which are associated to the phase theta. So this is a non-perturbative extension of the ideas of Nekrasov-Rosly and Shatashvili. Right. So what is important about well, one of the important things of the previous is that whereas this Borel sum could only be computed if we had a weakly coupled description of this superpotential, which we might not always have, because remember, for these four-dimensional n=2 theories, many of them do not have a weakly coupled description. But even without such a description, we can now define this new object W, which depends on U and theta, in terms of the quantum periods as before. So that definition can be extended to the whole Coulomb branch. So this relates to work by Bridgeland and collaborators, who express this W. So this W can also be seen now as a solution to a certain Riemann-Hilbert problem, which is specified by the structure of the BPS states in the corresponding theory. Let's see. So in terms of, well, maybe I'll go quickly through this because I don't have too much time, I see. So in terms of the field theory, you can interpret these boundary conditions, these Lagrangians, which were labeled by U and theta. You can also interpret that in terms of the field theory. And in terms of the field theory, it corresponds to coupling, at least in the four-dimensional case, it corresponds to coupling a three-dimensional n=2 theory to the boundary of this omega background. And in the simplest example, remember maybe these two, well, in the simplest example, which is this 82 example, where we had two of these branch points, and we had a critical phase, and we had the network, which changed by what is called a flip if you cross this phase. So this simplest example corresponds to coupling this four-dimensional theory to a three-dimensional theory, which is known as the theory corresponding to the tetrahedron in the work of Gayato, Kukov, and Dimovde. So the corresponding coordinates, if you work them out, before and after the flip, they correspond to a change in the superpotential, which is a dialogue. And this is going to be important. So this dialogue is exactly the superpotential of this three-dimensional theory corresponding to the tetrahedron. Because, well, all the coordinates that we find, all the Darboux coordinates, they're all generalizations of the coordinates in this example. So that means that so they're all what is called cluster coordinates. They're related by flips of this kind, and so all of them are related by a change of the superpotential with such a dialogue factor. And so that implies that this object W, which depends on U and theta, that it can be seen as a section of a certain line bundle over this modular space of flat connections, which has these dialogues as its transition functions. And this line bundle was studied before, and it's known as, in particular by Andrew Neitzke, and from another perspective by Alex Wandorf-Person and Pierre Lieb. And so that means that this line bundle is known sometimes as a classical Chern-Simons line bundle. So there is also a very nice geometric perspective from the perspective as a line bundle over this moduli space of flat connections. Right. So very briefly. So I wanted to show you two examples. So one of the nicest examples in 4 dimensions is just this cybercritin theory. So in the cybercritin theory, as we've seen before, the Coulomb branch is parameterized by a single parameter u. You might know that this Coulomb branch is divided into what is called a recoupling region and a strongly coupled region, which are divided by this wall of marginal stability. Here is a diam point and a monopole point, where one of the BPS states becomes very light. So in the weakly coupled region, we have a spectrum which is characterized by this phase diagram. So there are there's an infinite set of BPS particles, and the corresponding phases, they accumulate at a certain phase, which we called the Vengeful-Nielsen phase before. That was the phase of the W boson. Whereas in the strongly coupled plane, we have just the diam and the monopole. Right. So everywhere in this, to every point in this Coulomb branch, we can associate this object W of U of theta, which also depends on theta. We can compute it actually, and it forms a nice section of a line bundle over the corresponding moduli space of flat connections. So this can all be computed very explicitly in this particular example. The next example is the resolved conifold. So maybe I can use 2 minutes to say something about that. So, so the resolved conifold geometry is exactly the geometry corresponding to this toric diagram that we've seen before. In terms of the cybercritin curve, so the cybercritin curve is a fairly simple equation in terms of y and x, where q was this exponentiated scalar parameter. And so what I want to do is I want to consider it as a covering, but just a covering with one sheet over C star. And yeah, so as I've mentioned before, this corresponds to 5-dimensional U1 gauge theory on R4 times S1. So in this case, the NS partition function is very well known. It has this particular form. Also, there are, the vacuum expectation values, there are solutions to this equation where this d of sigma, that was denoted as d of epsilon before. So this is this quantum curve, which in this case may be parameterized by this difference equation. So there is one sort of solution which is, well, special in the sense that it appeared a lot in older works, which is a ratio of dialogues, which are these infinite products. But as we've seen from the following, it's much more natural to consider the Borel sum of sort of the formal epsilon expansion of this object. And this Borel sum will then depend on the angle theta in which we Borel, so the direction in which we Borel sum. So this Borel sum can be computed explicitly, as was done first in this paper by Validis and Kashav. And so what is really nice is that the jumps of this new object, they exactly encode the 3D particles, which are coupled to the surface defect. So remember, this was a surface defect VEF. So suppose we insert our brain at some point x in this geometry, then there will be certain BPS states which couple to this brane, and these objects, they're bound states of the two branes, of a D2 brane and D zeros. So we know their central charges. We know at which phases the Borel transform has its singularities, and this exactly matches. So this is an example. I won't have too much time, unfortunately, to explain this, but so indeed, so the jumps in this object, in this vacuum expectation value, they exactly correspond to the jumps of the spectral networks, of the exponential spectral networks. Right, so I won't say too much about this. But I will say that there are two special phases of this Borel sum. So there is, on the one hand, there is what we call the Gopa-Kumafava phase, and there is the non-perturbative phase. So it turns out, so if you write down, well, if you make a picture of the phases of these critical phases, then it looks something like this again. So the non-perturbative phase is the real axis, and the Gopa-Kumafava phase is where lots of these phases accumulate. At the Gopa-Kumafava phase, our psi takes the form of the original Gopa-Kumafava Gopa-Kumafava expectation value, and at this non-perturbative phase, it has a more complicated expression involving non-perturbative factors in epsilon, and this is known as a Fadeev quantum dialogue. And moreover, for every jump that we make, every jump across each of these critical rays corresponds to losing a factor in this expansion. Right. So similarly, we can compute this W. In this case, because we have an expression for W, we can compute it in two ways, namely just as a Borel sum of the expression that we have. And there is again this nice picture that everywhere where the Borel sum is makes a jump, we find a 5-dimensional BPS particle. And what we see is that in this case, we will see that there are again these two special phases. There is the Gopa-Kumafava phase, where the expression reduces to the Gopa-Kumafava expression that we already knew. And there is the non-perturbative phase, where there are non-perturbative corrections in this sense. So this is very much related to non-perturbative expressions that were found before, for instance, in the paper by Grossi, Hatsuda, and Marino, except that this expression is now, so it's in the half omega background. And so in this half omega background, it turns out that this non-perturbative expression, it has this exact self-duality property if epsilon goes to basically 1/epsilon. There was the other method in terms of the quantum periods, which is really important if we go to more intricate geometries, which is by evaluating the exact quantum periods, and by relating the B period to this object, W, to the superpotential. In this case, it's slightly subtle because the B period is non-compact. So there is a certain extra factor that we need to add in to make this quantum period, to make it well defined. But if you do that, then exactly this relation holds, and thereby it's a non-perturbative generalization of a paper by Akanagi, Sheng, Dijkgraaf, Kreffel, and Vafa. So this sort of completes the picture, at least for the resolved conifold. Yeah, sorry, I'm going over time, but yeah. So well, here is basically the conclusion. So we've defined a non-perturbative superpotential. So it's a new object which depends on U, some parameter in the Coulomb branch, as well as a phase theta. So that was really, really important. And so this has this object has a geometrical interpretation. You can see it as a generating function of these certain OPER connections or quantum curves, maybe. In terms of generalized cluster coordinates, it may also be defined in terms of quantum periods. So that's through exact WKB analysis. And so what is interesting about this object, so one of the things is interesting is that it encodes the complete BPS particle in its jumps, and that it transforms as a section of a distinguished line bundle over the moduli space, the Coulomb moduli space of the corresponding gates theory. Yeah, so I would like to stop here. Sorry again for going over time.
Thanks very much, Lotte.